Okay, hello and welcome to my channel. Today we're going to be solving problem 4, set 3 from MIT OCW course 805, Quantum Physics 2. Okay, so let's begin. Let's see our requirements. First is that you're given a real basis. So I'll just write real a dot b is less a b dot b. Or another way to write this, a dot b absolute less than a b. So next you're given a sort of guidance on how to prove this inequality. So this considering a minus lambda b for lambda is real. Okay, another thing is f of lambda is equal to a minus lambda b dot a minus lambda b. This is greater or equal to 0 for every lambda. Okay, and when is inequality saturated? All right, so this is A. Next is B. B is basically the same thing, but you're going to do this in the complex plane. So everything just exactly like A, but this time you got to consider the complex conjugate and stuff. So I'll just write it briefly. Okay, use V of lambda. What is that? Yeah, V of lambda minus lambda b with lambda complex. F of lambda now is equal to bracket V of lambda. All right, greater or equal to 0. When is inequality saturated? Basically the same. Next is C. C is you're given a complex vector space. Again, you gotta prove A plus B is less than absolute A plus absolute B. Okay, so prove this using the absolute real of Z is less or equal to absolute Z. Okay. Show that this holds. Show that this equation holds if and only if A is equal to a constant C times B, with C is real and positive. So C is real and positive. Right, so these are our requirements. Let's begin. A. First, we're going to consider f of lambda. So f of lambda is given to be A minus lambda B dot, dot A minus lambda B. Okay, we're going to expand this A dot A minus lambda a dot b minus lambda b dot a plus lambda squared b dot b. Okay, this can be rewritten again as absolute a squared minus 2 lambda a dot b. Maybe I can write 2 lambda a little bit better, plus lambda squared absolute b squared. This is greater or equal to 0. Okay, so here we're trying to prove an equality, specifically the Schwartz inequality. So when you have something like this, and if you want it to be saturated, meaning you want the equal sign, basically this is sort of the same as finding the bound in variational analysis, what we did back in a old problem in a old video. Don't remember what video it is, but this is basically finding bounds. So when finding bound, you take the derivative of the functional to equal to 0, and then you're gonna find the minimum of stuff. Okay, so should I know? Take df of lambda over d lambda to equal to 0. Alright, so from here, get that part is gone. Okay, that yeah. You get 2 minus 2 a dot b plus 2 lambda absolute b squared equals 0. From here you get your minimum lambda to equal to a dot b over absolute b squared. So from here you're gonna substitute this minimum lambda back into this. And so 1, 2, get that absolute a squared minus 2 lambda, now substituted with the minimum lambda instead. B, this is b, a dot b plus a dot b over absolute b squared on absolute b squared. This is greater or equal to 0. This part we can simplify it. This part can be grouped. So let's just do this slowly. A minus 2 this square, yeah, square. So b squared. This is to the 4th. So this is b squared, 4th, and square gonna cancel, give you only absolute b squared in the denominator. Okay, these two can be grouped. Minus 2 plus 1 is minus 1. Okay, so now it can again be rewritten. Minus 1 a dot b squared over absolute b squared greater or equal to 0. Okay, so from here you just switch the sides, and you're gonna get a squared b squared minus a dot b squared. It's gonna be greater or equal to 0. Alright, so these can be expanded into a dot a and b dot b. This has a minus sign. We threw these over here and switch the inequality sign. Okay, so now we have a dot b squared is less or equal to a dot a times b dot b, exactly as the requirement said. Okay, Okay, we got this. Now we're gonna solve next question, which is when the inequality is going to be saturated. So saturation happens when the thing is equal to 0. So f of lambda is equal to 0. F of lambda minimum. So take f of lambda equal to 0. We look back here. So what would make this 0? It is pretty obvious. You would need your a vector to equal to lambda b, right? So that is problem A completed. Okay, oh, sorry. Yeah, a new piece of paper. Okay, so now we move on to problem B, which is basically the same, but now we're going to operate in the complex space. All right, so let's just do that. Write out our f functional. This is greater or equal to 0. Now we expand lambda AB minus lambda star BA. Lambda star lambda B. This is greater or equal to 0. Right, so here we're going to take derivative of functional to equal to 0 to find minimum. And so from here you get that derivative of lambda. Okay, maybe derivative of lambda star is better. The star, then this gone. That is, yeah, those two are gone. So only BA plus lambda BB equals 0. From here you get your lambda minimum equal to BA over BB. Okay. So you can also get your lambda star minimum. You flip the thing, but the denominator, if you flip it, it doesn't matter. So only the upper thing got affected, which would give you AB over BB. Okay, so now we got this. Now let's substitute it back to our expansion right here. Let's go 3 and 4. 4. Get that A minus BA BB AB minus AB BB BA plus AB. BB. Okay, so this whole thing is greater or equal to 0. A bit crooked there, it doesn't matter. Okay, so from here, let's see what we can do. 2 in the middle can be eliminated. Okay, so these are gone. Okay, so this part, you gotta get down is BB square. Deal with the upper part first. Let's deal with the whole thing first now. Okay, this is gonna equal to AB BA. BA is technically just AB star, so you can substitute it for AB star. And AB times AB star is gonna give you absolute AB squared. Okay, absolute AB squared over BB squared. Okay, BB squared, and the BB up there is gonna give you, right, AA first plus, no, plus, no, it's a minus. Yeah, it's a minus. That cancels. So what you're left with is just absolute AB squared over BB. This is greater or equal to 0. And so from here you do exactly as the A problem. You switch the side and get your inequality that needs to be proven, which is this. Alright, so now we have proven our inequality. Now let's get the saturation. Happens when f of lambda is equal to 0. Therefore, take a look at this part. You would see that that would happen when A is equal to lambda B. There we go. That is probably completed. Next, we're gonna move on to C. C, you're given a complex vector space. Prove that. Okay, you prove that from using A plus B squared. So let's start from A plus B squared. This is gonna be A plus B, A plus B. Okay, now this can be expanded into A squared plus B squared plus 2 real parts of AB. Alright, this is just a formula, nothing there. Okay, now follow the guidance. We're gonna be using the real part of Z is less or equal to the Z itself. So from here you're gonna get that real part of AB less or equal to absolute AB. Okay. So this is an upper bound for you. So from here you get that absolute AB squared is less or equal to A plus absolute A squared plus absolute B squared plus 2 AB. Okay. From here, let's take a look at the Schwartz inequality. Wait, do we have to do that? Do we have to do that way? Here we can just, right, what? Yeah, we can just jump straight into the saturation part. So let's say that with saturation, with not really, with just we have. Right. So we have that when saturation happens, real AB is going to be equal to absolute AB. And this would force your AB to be real and greater than 0. Okay, so AB should be real and greater than 0. Okay, and AB is also equal to lambda BB, which is just B squared lambda star B squared. Okay, so this is what we have. You're asked to prove that this. Oh wait, I forgot to prove it. Oh my gosh, I'm sorry. God. Okay, I forgot the proof part. That's my bad. Okay, so now we're gonna go back to here. Go back to here. So from here, we're gonna use Schwartz inequality, which is absolute AB is less or equal to absolute A times absolute B, meaning that now we put a 2 in, doesn't affect the inequality, is still the same. B. So you get that your AB squared, your A plus B squared, is going to be less or equal to absolute A squared plus absolute B squared plus 2 absolute A times absolute B. Okay. Which is just equal to, this whole thing is equal to absolute A plus absolute B all squared. There we go. Now we have proven the inequality. There we go. Okay, so now we're going to go back to this part. So this is what we have right now. Okay, so 3 holds. This holds. You would need this. So for star to hold, you would need lambda star absolute B squared to be real. And greater than 0. And this happens when two requirements. Lambda star is real and absolute B squared is real, and this is always right. So this has to be real and greater than 0. And this is always right. If lambda star is real and greater than 0, then you can say that lambda star is equal to C, which is real and greater than 0. Okay. Therefore, you can say that A has to be equal to C times B, where C is a real and positive constant for this to hold. Right, and that's it for today's video, and goodbye.